Okay, good morning and welcome. Hi, this is section 8. Thank you for being here. Um, Here's the QR code. Oh, oh. One more time. Here's the QR code. Thank you for filling it out, letting me know that y'all are here. I forgot what the question is for today. Study spot, yes. Um, so, some announcements off the top things. For the people I met with yesterday, it was lovely meeting with you. For the people I'm meeting with today or tomorrow, I look forward to meeting with you. We are having meetings. If you have not signed up for a meeting, there might be 1 or 2 slots left open that you're welcome to sign up for. If not, or if it doesn't line up with your schedule, email me. I would still like to meet with you, even if you couldn't make one of those, and we'll find a time and make it work. Mid-semester feedback. So about 15 people have filled it out already, and in 1 day. So, but I comb through it, and we again take it very seriously. Everything that you write will be read. So I have realized a couple things. One, I've been too precious about the annotated section notes because I'm I want to only deliver typeset, blah blah, really beautiful notes. Y'all just need the answers to things, and so that's something that when I get an hour and a half, I will just write physically on it and upload, so there will be annotated, and that should be within the next day or so. I'm going to try to add roughly 10 more extra help room hours. Again, that's not part of our contract. We are only paid for a certain amount of time, but y'all need more support. Luke has to miss lecture tomorrow for an interview, so I'm going to see if he can offer some more help room hours too. So we will try. In terms of the scheduling, I know that I am completely booked from 8 a.m. until 11 p.m. until Wednesday. So I will be offering extra office hours on Wednesday next week. And then I will be offering a lot more during the last week of the class. Other things, some of the feedback was the solutions are not detailed enough, especially for things like the practice exams. You're right, it's an answer key, not solutions. But Monday night, I set aside 3 hours where I'm going to just talk through the practice exams and record a video, so you'll be able to go and hear someone kind of talk through the question, which hopefully will be a helpful resource. Trying to think, there was 1 or 2. Oh, section videos. So I record all of my sections, and the policy from the beginning has been if a student asks me for a section video, I will send it to them. They just have to send me an email because I will not remember to send it. And the reason why I don't just post it on Canvas is so that people actually come to section. But at this point in the course, people that are coming to section will continue to come to section, and people that don't won't. And so I'm just in the next day going to post the full playlist with all the section videos online, because that's going to be a useful resource for some of y'all. So again, we are going to be reading everything and trying to respond to as much of it as we can. There are some things where we get contradictory feedback of some people are help room is great. I thought I would hate working with my peers, but actually they're not that bad. And some being everyone else in the world can go and die. I hate help room. These are extremes. No one actually said that. Test me. Or some people are actually, I really wish that section was much more content and we did less practice. And some people are we're doing too easy content and too easy practice, and we need to be doing even harder practice in section. And so really it is kind of a balancing of different people want different things out of the experience. I still want to hear what you want, and whatever the majority is, I will try to adapt and go with that. Again, I know it's kind of late in the course, so there's not a ton that we can do, but we really care about the feedback. So, if you come to a meeting with me and one of the main things that you want to talk about is just grades, specific numbers of I'm trying to get this grade, and I know the strategies, I'm trying to do it, then what I will typically do is I will go to a spreadsheet that has this rough kind of grade calculator thing. Nothing is new on it that's not on the syllabus. It's not some magic code. It's just a spreadsheet that you can make a copy of and play around with numbers and see what you need to make on the exams to get whatever the final average you want. So, yes, that is here for your reference if you would like to go through that. Any logistical questions before we jump into section, proper? You should. It should be any other of your previous courses, but You should have access. Like, I still have access to the classes I took in 2016, or the ones I did summer 2019. So, if I lose that one day, I'm going to be really sad. Cool. Any other logistical things? So, this is the document that I made that I'm most proud of for the class. I just think it looks nice, and it summarizes all of the alkene reactions. The alkene functional group is the one functional group that can turn into the most things. And so this is probably a lecture where it does feel a little bit spread out of, like, there are so many things that we can do with alkenes. This is the most. Everything else can only do fewer things. So this is the biggest reaction web for this class. And I've done some, like, color coding to group them into families where if they're the same color, they react similarly. I have, like, mechanism notes here. It really is a true, like, one sheet of, like, I need to do alkene reactions. I would go to this sheet until I have it completely memorized, you know. So I think the big thing that I can do to help you with this, like, sea of reactions is give you some kind of structure and organization of them, so that you know what to pay attention to and you know how to group them. So I'm going to start with the first big delineation, which is this kind of line here, which I don't write explicitly. But everything to the right of this line, I call the simple alkene additions. These are your kind of basic, most straightforward mechanisms that are kind of foundational for alkenes. These are some of the first ones that you learn. And these are the ones that you are going to be, like, tested more on kind of mechanism-wise, or have some more kind of intricacies in terms of, like, the actual reaction itself. The ones on the left I call complex. And these are ones where you typically mostly just need to know them as line reactions. In some cases, we've given you some mechanism details, but I truly don't think any of these on the left side have, other than, the radical one, which radicals kind of fall into section 9, and so I'm not really talking about radicals today. I'm really just moving it to section 9. All of the other ones on this side of the page, I've never seen an exam that had a mechanism on it. And so I think that distinction of the kind of simple versus complex gives you your first big divider. And then within the simple reactions, we have kind of 3 major families. And so that kind of structure is going to guide our section, where we are going to talk about each one of these families and do some practice kind of back and forth. And then we'll talk about all the complex together. Cool. So before we really get into the nitty-gritty of the families, we need to talk about some kind of terminology and, like, lay of the land things with alkenes. So basically, for each of these alkene addition reactions, you have to answer 3 questions. Those questions are what, where, and how. So the what is just what 2 things are being added on each side of the alkene. And so for something like Br2, the 2 things that are being added are Br and Br. For, like, BH3THF, the 2 things being added are an OH and an H. And so for each of these reactions, you need to be able to reproduce what are the 2 things that are going to be added to the alkene. So that's just the what. Second question, where, is the regiochemistry. And for this, we have Markovnikov's rule. Our way of saying Markovnikov's rule is the more electronegative thing adds to the more substituted side. Some classes phrase it in terms of the hydrogen adds somewhere, or the less electronegative adds to the less substituted side. There are different ways of phrasing it, but ours is the most kind of comprehensive. Now, the more electronegative group is typically a nucleophile, and the less electronegative one is typically a hydrogen. That is not always true. But let's say that we had this alkene and we wanted to add our what of a hydrogen and a nucleophile. If we added our nucleophile to the more substituted side, a hydrogen to the less, we would say this is our Markovnikov product of who ended up where. The nucleophile, which is typically more electronegative, adds to the more substituted side. If we added the nucleophile to the less substituted side of our alkene, then we would call that the anti-Markovnikov product. And that is talking about, hey, we added this nucleophile over here instead of the more substituted position over here. The last question, how. The how refers to the stereochemistry of the 2 things that you're adding. And if you have a like double bond, like imagine I have a double bond here, my p orbitals are going to be above and below that double bond. So I could either add both things above the double bond or both things below the double bond. And just having them both the same way, we call that syn. So both above, both below. And we can represent those as both on wedges, both on dashes. So that's syn orientation. Or we can do one on a wedge, one on a dash, or vice versa, one on a dash, one on a wedge. And that's the anti-orientation. So at this point, we have a little dance that we're going to do, which is called the syn-anti dance. And it's just to remind you what these terms mean. So it's a little silly, but it's syn, syn, anti, anti. Do you want to see it again, or are you ready to do it? One more time. Syn, syn, anti, anti. You ready? Ready, go. Syn, syn, anti, anti. Now you remember syn and anti, and you'll never forget. I also just tried to do some diagrams here showing like, oh, okay, these are both adding up or both adding down, just to represent it in a few different ways. The one kind of warning is you don't always care about syn or anti. Like syn or anti is an inherent part of a reaction. Reactions can either be syn, anti, or a mix of syn and anti, and you need to know that for each of the reactions. But sometimes you just don't make stereocenters. Like in this one, this is not a stereocenter because it has two methyls, this is not a stereocenter because it has two hydrogens. So like you don't need to worry about wedges and dashes in stereochemistry, and like it doesn't matter if this reaction was syn or anti because you have no stereocenters. So it's kind of a thing where you need to know it, but you might not always have to use it. Last thing to watch out for is ANTI you see in both anti-Markovnikov and anti-stereochemistry. They do not mean the same thing. You can be a syn addition anti-Markovnikov. You can be an anti-addition Markovnikov. So just be careful with those. Any questions on this terminology of the what, where, and how for the alkene reactions? To help you out with those ideas, I have put the what, where, and how outside of each of the bubbles. So, why did I write quote Markovnikov here for the one that adds bromine and bromine? Because they're the same. There isn't a more electronegative one to add to the more substitute side. Yeah, but it roughly follows Markovnikov's rule. Cool. Okay, are we ready to jump into the first family? Do we want to transition, or are we over the transitions? Okay, let's see. So simple alkene additions. So this is our first major family of the simple additions, and they start off with a protonation event for the alkene. So the alkene's going to go grab a hydrogen, and we have two options. We could either add a hydrogen over here, or we could add it over here. So between the left and right, which one is the one that's going to actually happen? We love a smattering of answers. The left. The determining factor is the carbocation stability. So over here, this is a secondary carbocation, whereas over here, this is primary. Secondary is more stable, so that's the one that is always formed. So we now have added a hydrogen, and we have a carbocation. And at this point, some nucleophile is going to go and attack. And here I wrote this like initial acid as HX, where X could be bromine or chlorine, so we could have HBr, we could have HCl. Or this could be like H3O+, where you have H and then OH2. And so in that case, OH2 would be the thing that would come and attack. You could also have this be a protonated alcohol, so that would be a positive charge, and then the alcohol would come and attack. But the essential kind of formula of this reaction is alkene grabs a hydrogen, you make a carbocation, nucleophile attacks the carbocation. Here there might be a deprotonation step, but this is the basic idea. That's true for all of them. Yeah.
So, in a lot of those steps that we presented in the course, we always like protonate first.
Mhm.
And is that because it's a better electrophile than it's a
It's because alkenes on their own are not good electrophiles.
Okay.
Alkenes are nucleophiles. They are the ones that are going to do the attack.
Right. So we turn it into an
Exactly. Yep. Cool. So stereochemistry here. We are going to get a mix of syn and anti, and let's see why. So we have deuterium here, which remember is just an isotope of hydrogen. So if this is just kind of like a hydrogen, which side is more substituted, the top or the bottom? The top. It has more carbon things, it's more substituted. So we know that this is going to go and grab a hydrogen, and our hydrogen is going to add the bottom to make our tertiary carbocation up top, which is more stable. And here, remember our double bond, we have our p orbitals above and below. Our alkane could go and grab a hydrogen from above, and then it adds on a wedge, or it could add a hydrogen from below, and then it's on a dash. So we already have two options here. And then we have a carbocation. Now, what do you remember about carbocations in stereochemistry when we talked about SN1? About carbocations in stereochemistry. So, we have an empty p orbital, right? And with this empty p orbital, I'm actually going to draw that in a different color. Our nucleophile could come in and attack that empty p orbital from the top, in which case we would get the nucleophile here on a wedge. Or our nucleophile could go and attack that empty p orbital from the bottom, in which case it would be on a dash here. And same thing for the carbocation at the bottom. Our nucleophile could attack below, and then it's on a dash, or it could attack up top, and then it's on the wedge. And so if we look at the two things that we added of our nucleophile and our hydrogen, we can either have the version where these two things were added syn, both on wedges, both on dashes, or anti, where they're flipped. So we get a mixture of them. We would get 4 separate products. Now again, with something that is as simple as this, with like H3O+, you would only get one product because this has no stereocenters. So you don't always have to worry about this, but I want to show you the complicated version so you know kind of the hardest thing that you could see. One other thing real quick is, do you remember the plus-minus notation system that we used in the past, like where we wrote this? That means the molecule plus its enantiomer. So if you, instead of writing 4 things, wanted to only draw 2 things, so let's say I didn't draw this, I could draw the ones above with plus minus, and that would represent the same 4 products. And so this is the way that, like, functionally you're probably going to do it if you ever have to do something like this. Yeah.
That's
Cool. I was like, yeah, I have a feeling. So that's the stereochemistry side of this. We get mixture of syn and anti. The other thing with carbocations is they do funky things, as you all well know after that problem set. So here, if we have this molecule with H3O+, we formed a carbocation in the first step. It's a secondary carbocation adjacent to a quaternary carbon. So what's going to happen is a methyl shift. Then our carbocation moves over here, and then water adds. And so we get this product where, like, the OH and the H, like, do you even call that Markovnikov anymore if there's a rearrangement? Like, kind of not. But basically, you just always, if you are doing a reaction that has a carbocation intermediate, you need to draw the carbocation and check for a rearrangement. That's kind of a hard check that needs to be done. Here's just a summary where I put the 4 kind of flavors in this family together. And I'll write out the nucleophile for each. So for HBr, the nucleophile that would come and attack in this step would be Br minus, HCl would be Cl minus, H3O plus would be H2O, and alcohol and acid would just be the alcohol. So with this, let's do a couple quick practice that are not on the problem set. These are just ones that I made up that kind of get into the intricacies here. So I want you to try these 2 reactions and predict the products, all products with stereochemistry. About 30 more seconds. Welcome back. So, this first one, H3O plus, what two things does it add to an alkene? An OH and an H. And we know that this is typically a Markovnikov, and we know that we get a mixture of products. So whenever I see a line reaction for alkene additions, I always write the three things, just as a reminder to myself and so a way to kind of keep reviewing it. So we know that this is going to proceed through a carbocation intermediate, so let's draw that carbocation. I'm going to draw it up here. So the carbocation is going to form over here because that's tertiary, more stable than secondary, and the hydrogen would add here. Okay, do we rearrange? No. So it's a thing of, we're right next to this very alluring tert-butyl group. But if this rearranged and you did a methyl shift, you would still only have a tertiary carbocation. And so, like, there's no reason for it to do that shift if both of them are tertiary. Yeah.
And it wouldn't have broken, it wouldn't be two groups that could go in the same structure. Like, could it still happen?
No, well, because it wouldn't be resonance. Like, resonance would be, like, delocalizing, where, like, the actual structure is bonding across three atoms. Whereas rearrangements, we're talking about different molecules. Yeah. So, yeah.
So I'm a little confused about how we can say it's a mix when each.
We're about to get through it. So the second question is here, this carbon, is that a stereocenter? No, we added a hydrogen to it and it already had a hydrogen. So there's no stereochemistry there. We only have one stereocenter in this molecule. So our product is going to look like, we add the OH here. And we'll have the version where OH is on a wedge and version where it's on a dash, because we go attack the top or bottom face. So this would be the correct product with stereochemistry. And if you drew the dash version here, and like you put this on the wedge and you still have the plus minus, you've written the same thing, so you're good. Because this, your nucleophile could attack the top or the bottom. Okay, for this other one, HCl, where are the two things it adds? It's HCl, so yeah, it's an H and a Cl. We love the energy this morning. Woo. We have a Markovnikov, we have a mix. Which side is more substituted between left or right for this alkene? Right is more substituted, so that's where we're going to have our carbocation. So we draw our carbocation structure with that. We have deuterium and hydrogen there, and methyl. Is this going to rearrange? No. Is the place where we had a hydrogen a stereocenter? It is. It has deuterium, hydrogen, and ethyl, and then the rest of the molecule. So we are going to get the 4 different products. We're going to get all of them. So the way that you can kind of easily and quickly write all of them out is just do one version where you've added your 2 things, the hydrogen and then the chlorine, both syn, where you've added them both on dashes or both on wedges. And then do one where you've added them anti. So here I'm going to keep the deuterium and the hydrogen the same, and now I'm going to put the chlorine on a wedge and methyl on a dash. And then you would write the plus minus for both of them. And that's how you could easily get all 4 products. There are other ways that you could have drawn this, certainly.
I didn't know like the deuterium and the hydrogen, or I know the hydrogen is going to be like either a wedge or a dash because you're adding them. But how do you know the deuterium is what you're going to put on a wedge or a dash versus the like straight on top?
Like, you can write it several different ways. I'm just trying to write it in the way that, like, you can clearly see the syn and anti. Because I could rotate this, and Yes, and we're going to get into the stereochemistry of that and why that's tricky in a little bit. Yeah.
And for the most substituted, I would just say that for the right, because carbons may
It's carbons make it substituted, but deuterium is basically a hydrogen. Yeah.
No, we don't really know exactly what this is.
Deuterium is like an isotope of hydrogen.
But it counts as a different element. Making
It counts, yes, it counts as a different identity, but it is functioning the same in terms of stability for something like a hydrogen. So like that's why this side is less substituted, because it functions like a hydrogen, but these are different and you would be able to measure the difference. And that's why deuterium is really helpful for teaching examples, where like if I just had a hydrogen here, you wouldn't have a stereocenter, and then this would be an easier question. Yeah. Cool. Yep.
For the first one and before, why is it that we've learned from two products and the next one from four?
Because here we have two stereocenters, where there we only have one. Yeah. Cool. Let's look at the second family here. So these I used to call the X2 anti-additions. Now I call the halogen anti-additions. If you think of a better name, let me know. I don't have a good publicist for her. So this mechanism is fundamentally different from the first one, because we have this weird little like reach around. So your pi CC is attacking the sigma star XX, where here these are halogens, either BR/BR or CL/Cl, or you could even do II. We just don't do the iodine version. And if we put electrons into the antibond, what happens? The bond breaks. So we have to draw this arrow where the bond breaks. But then it's the weird thing of this alkene is going and grabbing this halogen, and the halogen is coming closer, and it would be about to form a carbocation. It's starting to form a carbocation, and the halogen's like, I have so many lone pairs, let me just help you out and make a little bond. And we get to this intermediate structure that if it's a bromine, we call it a cyclic bromonium ion, and chlorine, cyclic chloronium ion. Again, everything has a name. You don't need to know these names, but it can be helpful to just be able to give them like a name, or to be able to kind of like say what it is. Now, what structures do these remind you of? What functional group? Epoxides. Specifically, they're kind of like epoxides and acids, because they have this positive charge here on the bromine. It has two bonds, it normally likes one. It's kind of like when we had the OH+. And just like epoxides and acids, our nucleophile is going to go and attack the more substituted side. Also, if our epoxide is going up, we are doing a backside attack and attacking the antibond, which is going to be beneath the plane of the page. So we see that here, for the epoxide going up, the nucleophile adds from below. So our two things, our halogen and our nucleophile here, are anti to each other in our product. Similarly, you could have formed your epoxide instead of going up. You could have done the epoxide going down, or I said epoxide. You could have formed the cyclic bromonium going up, or you could have formed it going down, in which case your nucleophile has to attack from the top and is on a wedge over here. So in this case, you only get two enantiomers. You get these, like, both of the anti versions, which you could just write as one of these with plus minus, and that's a lot easier. So we have several flavors of these. Like, firstly, we have the chlorine flavor and the bromine flavor. But then we can do these reactions in solvents, and that changes things a little bit. So we could do water, alcohol, solvent, and it changes things at this step. So this first step is going to be the same for every single one of them. But then imagine you did it with bromine, but you had a solvent of water. You would have a Br minus, and that Br minus could come and do this backside attack, but it is just simply outnumbered by the solvent. And so the thing that's actually going to do the backside attack when you have a solvent of water is water. And so you wind up with an OH on the more substituted side here, because the water is doing the attacking. Similarly, if you have an alcohol solvent, the alcohol is going to attack there, and you would call this a halo ether, because you have a halogen next to an ether. So, again, chlorine flavors, bromine flavors, and within that you have solvent subtleties. It's very like wine or coffee tasting. You need to get all the notes. Let's try practice with this. So this is one of the weird skill builders where instead of doing Br2 or Cl2, we're giving you an iodine bonded to a chlorine. and you need to think about, okay, which one adds to which side? Because we know we're going to be adding those two. And just as a recap, like, remember we called this, like, quote Markovnikov because they were both bromine. There wasn't a difference. But here, which one's more electronegative, the oxygen or the bromine? The oxygen is. Your more electronegative thing is adding to the more substituted side. So that's going to be true for this reaction. So the thing you'll have to figure out is which of these is more electronegative, which I give you here, and that's going to be the thing that adds to the more substituted side. So then which of them is going to form the ring? And that's for you to try out. I'm also going to write another practice problem that I'm just making up here for you to do if you've already worked this. So try this, and then if you have time, look at the other practice problem. So with the skill builder one, how'd you do? Our iodine is less electronegative, so it's going to be the one that forms the cyclic iodonium ion, because again, everything up there. And then the Cl minus is going to come and attack, and we'll attack the more substituted side. Now, why don't I have dashes or wedges here in this product? No stereocenters. Technically, I didn't even have to write wedges here. I could have done bonds. I just like when there are 3 bonds here, or like when you're forming especially like an epoxide or a cyclic like 3-ring, I like drawing the stereochemistry just to remind me that they have to be the same way. Because remember, things can still have wedges and dashes even if it's not a stereocenter. We just typically don't care. You know? The what?
Is it, would it be incorrect to have the chloride and iodine come back?
No. Yeah, that would be fun. Okay. This molecule over here, I know that some of y'all have been burned by the problem set where there was a functional group you want to react with and then the alcohol way over on the side. In those moments where you were burned, what was the tricky thing that happened? An intramolecular reaction. So let's see. So over here you add Br2, and it's going to form the cyclic bromonium ion. And again, you would have the wedge version, the dash version. Again, the ending one doesn't have stereocenter, so it doesn't matter too much. And here you have the Br minus around that could attack, but the other thing that you have around that could attack is this oxygen. And it is going to do a backside attack just because intramolecular reactions are faster.
Not because OH is better.
Correct. Correct. It's more of a speed thing. So here, I'll do some numbering. 1, 2, 3, 4, 5. I know that my product is going to have a 5-membered ring. And I'm going to draw these kind of double arrows here to be like, I'm not drawing the full mechanism. I'm just drawing key structures. So I'm going to draw a 5-membered ring with an oxygen. Number it 1, 2, 3, 4, 5. And which number needs to have a dangly bit on it? 1. Because 1 is going to be attached to this carbon and then the bromine. So I need to have carbon and bromine here, and then that is a stereocenter. So I'll have the wedge version and the dash version. Cool. Yeah. God, they're long. I forgot how long they are. So, our next family and our last family in the simple alkene additions is making alcohols. We already did this reaction over here where we added H3O plus and we had a rearrangement happen. It was technically Markovnikov, but rearrangement occurred. The mechanism for this was on the previous page. So we need a way of doing Markovnikov addition that does not rearrange. And we also need a way of doing the anti-Markovnikov addition. There should not be a space here. I know that it doesn't matter too much to y'all, but it bugs me. I just noticed it. So, let's learn some reagents to do this. And based on how I'm introducing these as line reactions, that might tell you some of the importance of how you'll be using these. Both of these will be used a lot in synthesis, especially. So, to do the Markovnikov alcohol formation with no rearrangement, use oxymercuration reduction. So you do Hg OAC2 with H2O, and the second step is NaBH4. You might be like, NaBH4, I recognize her. She's doing weird things. This is her secret double life. She's doing radical stuff. We don't touch step 2. Step 1, we do touch. Then, for the anti-Markovnikov addition, we use hydroboration oxidation. So that is BH3 with THF. And our second step is peroxide, H2O2, and hydroxide, OH minus. So let's get into the mechanism of these and figure out why they don't rearrange and why they do anti-Markovnikov for these two. So for the oxymercuration reduction here, we start off with the oxymercuration step, where HgOAC looks like this, and notably it has a lone pair. And the double bond's going to attack the antibonding orbital, so you have pi cc into the sigma star HgO bond. That attack is going to break one of the OAC bonds, and then it has a lone pair and it's going to reach back around. So what does this look like? What family? This first step. Maybe I'll give you a hint of the thing that's formed in the second one we call a cyclic mercuranium ion. This is like our family that we just did, the anti-additions with the cyclic bromonium. It's like an epoxide. This kind of 3-membered ring where something is positive on it, you will see several times in lectures 7 and 8 here, and they all react really similarly. Of some nucleophile can then go and attack the more substituted side. So in this case, your first step here was HgOAC and water. And water is going to be the thing that comes in and does the attack on the more substituted carbon here. And then, after deprotonation, we get to this structure where we have HgOAC and we have OH. And those two things were added anti to each other, just like the anti-additions for the halogen. But In our second step, the reduction, this does some radical chemistry, which you are not responsible for the mechanism or knowing really anything kind of related to it. But as a result of the radical chemistry, this stereochemistry relationship is lost. And so it's going to scramble the stereochemistry when it replaces the HGOAC with an H. And we are going to wind up with both the anti-product and the syn product. Also, this, just a note, this like organic mercury compound, this is like the stuff they warn you about in like the lab safety videos, where I still remember this like really sad documentary that they made us watch for one of the upper level chem labs about like this scientist who got like half of one drop on her skin and was dead a week later, and like was like aware of what had happened and like was saying goodbye to all of her family. It was a lot. And so like anytime mercury comes up and it's bonded to carbon, neurotoxin. Y'all will never do this reaction other than on paper. At the same time, my dad like grew up in deep south, like Georgia, and they would take like mercury thermometers and then like play with the mercury. And like mercury metal is like, that's not recommended, but that's not neurotoxin. That's not kill you. But I'm just like, gosh, mercury, the two sides. Yeah. Anyway, I'm about to tell you my two kind of most smooth brain mnemonic exercises, memory things of the entire course. Like really, I think y'all will lose some respect for me after this. So how do I remember that mercury is the one that does no rearrangement? I think about astrology, and I think about like someone asking you to make plans that you don't really want to do, and you were like, well, I would, but right now Mercury's in my 7th house, so I'm not going to rearrange my schedule. It's so dumb. It's so like there's no part of that that's based on life or reality, but I'm like, I don't want to rearrange it right now. Mercury's in my 7th house, so that's how I remember it, and it's really, really, really basic. There is one other flavor of this. So you see this is the standard one where we have H2O here. If we put an alcohol there instead, then what we get is, instead of an OH2 attacking, an ROH attacks. And so the thing that we wind up with at the end of the day is an ether. And just like that, we've encountered our last way of making an ether. Aren't you glad you know this? So many ways of making ethers. Everyone's favorite functional group. So that's oxymercuration reduction. Why doesn't it rearrange? That's kind of our big question. Well, we didn't form a carbocation. And so if we didn't form a carbocation, we are not going to rearrange. Unless you're that one weird challenge problem on PSET 4. Cool. Hydroboration oxidation. Here's the other smooth brain mnemonic. So hydroboration oxidation, you can call it HBO. What does HBO have on it? Well, it has movies. What's a movie? Well, the 2006 classic, John Tucker Must Die. And they don't like John. They're anti-John. So they might also be anti-Mark. So I would think I need to do anti-Markovnikov addition of an alcohol, anti-Markovnikov, anti-Mark, anti-John, John Tucker Must Die, HBO, hydroboration oxidation. This is what I mean, where it's just so silly. It's so silly. So let's talk about why it's anti-Markovnikov. So this one's kind of weird because boron, remember, she has an incomplete octet. So she has an MTP orbital. And so what you have happening here is your double bond over here, the alkene, is going to attack the MTP orbital. And then this sigma bond with the hydrogen is going to move over to the other side of the alkene. And you would get this alkyl borane intermediate. So we've added a hydrogen and a boron. And immediately, you would probably, on a first glance, be like, okay, we added the hydrogen to the more substituted side, so this is anti-Markovnikov, or like this violates Markovnikov's rule. But the actual electronegativity is here. Hydrogen is the most electronegative. And so hydrogen's adding to the most substituted side. Did we violate Markovnikov's rule? No, we followed it explicitly. This one's nice compared to the mercury because it's just one step. And then the oxidation step, the H2O to OH-, you are not responsible for the mechanism for that. All you need to know is it replaces the BH2 with an OH, and it keeps the stereochemistry. This is a syn addition in both of these steps because think about it this way: if your alkene is interacting with BH3, which is going to come over, and if it kind of comes from the top here, then both the pieces are going to be on the top because that's the face it's reacting with. Or if your alkene is here and BH3 kind of comes from the bottom, both of them are going to be on the bottom just because that's the face it interacts with. You don't have that backside attack like you do with the anti-additions. I really like this reaction, and so I've shown the oxidation mechanism here in case you're curious. This is one that you actually did in PSET 1, but we gave you all the structures and you were just drawing arrows. It does some weird things in it, but truly this is just cool facts about hydroboration oxidation that I like if you are interested. You will not test it on any of this. So with this, let's do the third practice here. So it's going to be providing a curved arrow mechanism for a oxymercuration and for hydroboration. And you're only going to do the mechanism for the first step because you're not responsible for the second step. For the first one, notice the trap that here we don't have water, we have methanol. So we're going to have the alcohol flavor of this. And then down here, instead of hydrogens, we have deuterium. Treated exactly like hydrogen, it just lets us kind of label things to have a specific product. Lastly, we have one of these short, like 2 to 3 step synthesis from challenge problem 1, where you're going to be trying to get to this molecule from this one. And so I'll give y'all maybe like 5-ish minutes.
mean, oh, he put it.
Alright.
Okay, I'm really sorry. But he put it to I didn't write the. I didn't. I'm pretty sure I didn't write the names. But I was saying, I mean, that's what. Because if once we get to hear it, like this.
But you showed it. So what is more authentic, Savon or the Imperial? Which is basically has which one is more?
That's what I'm doing.
So that could be more.
Is that really fun?
Could be good. Mm-hmm. This whole class stresses. Okay. So, how did I do? How did you all do with this? We're gonna talk about the stereochemistry of each. For the top at least, the way that they've drawn the product has no stereochemistry indicated, so that is a sign to you that you do not have to pay attention to stereochemistry. So I did like a full stereochemistry version here, where I was even a little bit more rigorous I need. Like here, this HGOAC on the end, that's not a stereocenter. I don't need to draw a wedge or a dash, but this is not incorrect. I'm really just wanting to focus on, hey, these two things are kind of anti here when they react. Yep, and then for the deuterium version here, neither of these are stereocenters, so you don't have to account for anything. So these mechanisms were really just kind of trying to take the prototypical ones and like translate them onto new molecules just to get it kind of in your hand a little bit. For the bottom one, what two things does it look like we've added to the alkene? Yeah, it looks like we've added an H and a Br. And were those things added Markovnikov or anti-Markovnikov? Anti-Markovnikov. So, we have just talked about so far only one reaction that does anti-Markovnikov. So let's do that one reaction. That's going to be the hydroboration oxidation because anti-Mark, anti-John, John Ticker must die, HBO. So, BH3, THF, H2O2, OH minus. That is just like such an ingrained thing that like I have like a trauma like automatic response to of like, yeah, I can list out the reagents for hydroboration oxidation. Don't make me do it again, please. So that makes this OH, anti-Markovnikov, add on the less substituted side. And then can we go from an alcohol to a bromine really easily? We can. What reagent? PBr3. Now you might be like, well, Colton, didn't we learn a reaction at the end of class where we could do HBr, ROOR, and do this all in one step? And it does anti-Markovnikov addition of radical, or it does radical chemistry, and it adds a bromine, anti-Markovnikov. It does. In this case, it's weird, and it's because they were next to a strained ring, so it would actually pop open the ring. That kind of radical stuff we're going to talk about in sections 9 on Friday. So just know that like that is a great idea, and hypothetically, if we didn't have a strained ring, that would be a totally fine answer. Yeah.
What did they say the first one you did too in terms of and adding the bonds?
Oh, this one?
Yeah, like where you added them. Like, I guess
Yeah.
I was getting confused as to which one was more electronegative.
Deuterium, which is basically hydrogen, is more electronegative than boron, so the deuterium adds to the more substitute side. Yeah. Cool. Okay. Now, we are going to do this together, the tricky alkene stereochemistry problems. This is something that's kind of intricate and it's nuanced, and it will be one box problem on the test, and like the average on that box problem will be like 40% in terms of getting the stereochemistry. It's just a tricky skill, and like you can get really close to the right answer even without doing this. That would only be like a 1 or 2 point deduction. So I'm going to teach you the hard thing, but just know that this is a trickier one. So for all 3 of these are from challenge problem 8, so these are a challenge problem. For all 3 of these, we are being asked to predict what the starting material is. So here, this is one that we haven't talked about, H2 palladium on carbon. It adds 2 hydrogens to either side of the alkene. And here we see that we have added 2 deuteriums here. So we know that the double bond needs to be here, right? Like, so we could easily draw a product with a double, or a starting material with a double bond. The hard part is it this one? Or is it this one? It's the stereochemistry of these 2 molecules. And that's the part that we are going to kind of talk through how to do. So I'm just going to do kind of question marks by them, and then by the end we will have one answer. So H2 palladium on carbon, if we do our analysis, it adds, in this case, deuterium twice. It is, quote, Markovnikov, because we're adding the same things. And the other big piece of information is it is syn. The way that this is drawn, do those deuteriums look syn? They don't. Like you can't clearly see it. We have to rotate it so that it looks syn to us. So what we are going to do, the strategy here, is I'm going to write it so that both the deuteriums are down and in the plane, because then I can clearly see them being syn. And so this, like, right deuterium over here is already down in the plane. So I know that I have a hydrogen here, and I have a methyl over here. For the other one, we actually have to rotate it. So here, it's down and away from you, so it's kind of like here. And we want it to be down and in the plane. So we're kind of rotating everything forward. So what does that do to this wedge that's down? It's now up, but it's still a wedge. And then what did we do to the ethyl that was in the plane? Well, it was in the plane, and we're kind of rotating this way. So now it's going to be away from you, ethyl. So now, in this orientation, we can clearly see the 2 deuteriums here. And they are syn. And so we can use the wedges and dashes to tell us what's cis and what's trans to each other. So here, these 2, the hydrogen and the methyl, are both on wedges. So the hydrogen and methyl need to be cis to each other. So here, This would be the version where the hydrogen and methyl are cis to each other. And then the two things on the dashes are the ethyl and the methyl, the other methyl here. And so we know the ethyl and the methyl have to be cis to each other. So we know it was this alkene.
You said that last diagram, that why would it be 6
It's because when you have written it to where the two things that you added are in the plane, whatever two things are on wedges together, they have to be cis to each other. Whatever two things are in dashes together, they have to be cis to each other. It's just kind of like an easier way of doing it. There are several other methods that could be done. This is the method that works the most for me. But there is a far easier way if you use your model kit. So I will show you the model kit version as well. For this, I'm going to do some highlighting. So, what I've built here is the blue is going to be the deuteriums here. And you see how this deuterium is straight down and this one is down and going away from you. And the other color I want you to pay attention to is the red, which is going to be the methyls. So on this carbon, the methyl is up and going away from you. And the other carbon, it is down towards you. Do you agree that this is that molecule? Cool. What we can do is we can rotate it to where our two deuteriums are syn to each other, where we can clearly see it. And this is my favorite thing. You can just fold it, and you see that the two methyls have to be trans to each other. And look at the product, the two methyls are trans to each other. So I'll do it again. So we have built this, which is the molecule. We rotate it to where we see the two deuteriums syn to each other, which is the stereochemistry of the reaction. And then we fold this in. And again, it's kind of fighting with the geometry of these like bonds. But when we fold this in, like we were making a double bond that came before, we see now the two methyls are going to be trans to each other. It's a lot. That's why you're going to do a couple practice. So these are also from the same page of the problem set, where your process is you need to look at each of these reactions, ask what two things were added, and were those things added syn or anti. Once you have that information, you need to draw it so that the two things, if it was a syn reaction, are both in the plane, like your thing 1 and thing 2 are in the plane, and then you can use the wedges or dashes and figure it out from there. Or if it was anti, you need to draw them both in the plane, thing 1 and thing 2, and then the wedges and dashes tricks work. Or you can use a model kit. I would say if you do not have a model kit with you, which I'm not seeing many model kits, try the wedge and dash first. So it's about the alkene. The side that is less substituted has more hydrogens. So which side has more hydrogens? That's the less substituted side.
just helps you determine what the
So, this reaction, I2, that's a BR2 or CL2, is to add sin or anti. The way that you draw the eyes, it's sin. So you have to draw the eyes anti. You're doing okay.
Oh wait.
Yeah, so that one's really easy. You don't have to do hard work.
That's how the reaction.
And the next one is harder.
Okay, this is
Okay, the first one is not meant as a trick question, it was meant as an easy question. So, the I2, what two things does I2 add? I and I, and then does it add sin or anti? Because BR2, CL2, I2, they're all in the same family, and that family is called the halogen anti-additions. So that's kind of where we got that information. The second step would be trying to get the two eyes in the plane opposite each other, anti. They are already in that position. You do not have to rotate it. And so it's whatever things on wedges are cis to each other, whatever things are dashes are cis to each other. So here, the ethyls on wedges need to be cis to each other. And then the hydrogens on dashes need to be cis to each other. I mean, you don't have to. Again, when we're doing this kind of detailed stereochemistry stuff, I think it's helpful, but
Can you explain one more time what the squeeze is about? Because I have not.
have you built it? Can I see it?
Oh, okay.
So, the red ones you did is the iodine, right?
No, is the answer is fine.
Okay.
But we can work it out.
Uh,
But what it
let's actually do it.
Okay.
Yeah. So here, the white ones are the iodine, and here are the alkane. What you would do is you would fold the two white ones in, and oh wow, yours are really, really. Oh gosh. I can see now that my models have been very born in, and it might be harder to do on yours. But you would take the two things that are supposed to be anti and fold them in to make the double bond, and in this double bond, yes.
Why am
Okay.
So sorry,
That-
that's.
Thank you.
Do you want us to just do the last one together, or do you want to try it? I'll give you all like a minute or two to try it, just to see. For the bottom one, I think you will have to rotate.
Okay.
So, no, for this, if it's sin, they have to fold in the same. Like here, they have to fold into the double bond, both coming together.
Okay, that's what we're doing. You said there's
And
so
we're
much
anti.
one top on bottom.
Exactly. So like the anti-folding is much harder.
Okay. You see, like, okay, okay.
Let's just say that I'm gonna go with this one. I mean, if I had to do this, we could just pretend it. What would be the more sensitive?
This middle?
So
He-
if you wanna draw it, the eyes are the same way.
Yeah, and these eyes are on the same plane. They're all in the plane of the paper. They're not on wedges or dashes.
Okay.
So it's, it makes me just think I can be here rather than what do you mean if rotate it backwards?
It's when you've written it this way, if it's an anti-addition, and one's top, one's bottom, and they're in the plane, that has accounted for the anti-stereochemistry, and you can just go with what's on wedges is cis to each other, and what's on dashes are trans to each other. It's kind of like making, like, what if our double bond was here in the plane? Like, if our, gosh, it's hard to do this, like, spring-loaded version. It's if our, like, alkene was the plane of the page here, like, one thing would add forward, one thing would add back if we were doing anti, or they would both add forward if it was sen. Yeah. So BH3THF, what two things are added? H and OH, and is it a syn or an anti-reaction? Syn. So we need to do something to make sure that our OH and our H are in the same plane, going the same direction. So I'm going to start off with the right carbon here. The way it's written, it's up and it's away from you, and you can rotate it forward. So it's up and away, you rotate it forward. So when we have that, the hydrogen that was already up and forward now becomes down and forward. And then the ethyl, which was down here, gets rotated back. Okay. And then down here, our hydrogen was on the wedge, and we needed to be up and in the plane. So this one's a little bit easier to me to do kind of like on paper, because I just know that the hydrogen needs to wind up here, then the ethyl would rotate back, and then the methyl would rotate up. Like I'm just switching where these three things are. So the hydrogen is up and in the plane, then down in the dash is the ethyl, and on the wedge comes the methyl. So the way it's drawn now, we see clearly the syn stereochemistry. The two things that are on wedges are the methyl and hydrogen that need to be cis, and the two things that are in dashes are the ethyls that need to be cis. So the way I would draw it, here, and then methyl. Where here are ethyls, and here are methyl hydrogen. If I do the kind of building version of it, I'm going to call, I think, the OH and the H blue. And then I'm going to call my ethyls green, I believe. And this is just like to help me with like the labeling with colors. So here, my ethyls are the green. Here and here, they're in the plane. Here, the blue OH is over here, and then the blue H is over here. So away and forward. Do you agree that this is the same molecule? In terms of these green ones are the ethyls in the plane, the OH and the H are the blue. What I then do is I rotate so I see it being syn for the blue things, and then I fold the blue things in, and the two red ones are cis to each other, and those were our ethyls, or the green ones. They're both cis, whichever way. But this is the hardest one. If you drew the wrong alkene, that would be a -1 or -2, so don't stress about it. But it is like the hardest type of stereochemistry that we can ask for this. It will be one box problem on the test, not more. Because of that, I kind of don't want to spend more time on it. I want to make sure that we get to some of the other stuff. So other questions with this, I'm happy to answer at the end. But let's keep chugging along. So all of this was on the simple alkene reactions. The complex ones you mostly need to know in terms of like functional groups and line reactions. Ozonolysis is the first one here that we'll talk about. It is a really, really big, useful reaction, mostly because it does funky things. Like it can break open a ring and create these functional groups on either side. If you had an alkene that was in like a long chain, you could do ozonolysis and it would break the chain open. Basically, what you are doing is you are chopping up the double bond and you put a carbonyl on either side. So that is the baseline what you do. And we have two sets of conditions that we can do this reaction in. So one of them is with our second step being H2O2, which we would say is oxidative conditions. And the other one is with the second step being dimethyl sulfide, or DMS, which we would call reductive conditions. So if we are doing it in reductive conditions, once we break the bond and add the carbonyl, we are done. That is the reductive product. If we are doing it in oxidative conditions, we have one last step, and that's we look at our two carbonyls, and if we're in oxidative conditions and one of them was an aldehyde, you turn that into a carboxylic acid. You just add an OH instead of the H there. So let's do this kind of disconnection over here. Maybe I will do this middle one because I think it's a little bit harder for y'all. So, first of all, if I was doing ozonolysis, does it affect a benzene ring? No. You'll have not learned any reactions for benzene. You will learn that tomorrow in lecture 9. So the alkene that's going to react is this one down here. What we are going to do is chop it in half, and then we are going to put carbonyls on either side. So let's try to draw what that's going to look like. So this would be our reductive product, our 1,N-DMS, where we've just split open that bond and put carbonyls on either side. One of them is an aldehyde, one of them is a ketone. To get from this reductive product to the oxidative product, I just take the one that's an aldehyde and I make it an OH here, so it's a carboxylic acid. And I'll draw that a little bit nicer. And that's how you predict the products. So can you take truly 90 seconds and try to disconnect these two and do the reductive version and the oxidative version? So how do I do with the disconnection? I know it's real quick. This is the extent of what you'll need to do with ozonolysis, of just being able to know whether or not you want the reductive or oxidative and what's the difference, and then being able to write the product. There's no mechanism. I think Tim showed some arrows for this. We never test the arrows for it. The second reaction, which we're not going to spend much time on similarly, because it's mostly a line reaction, is the osmium tetroxide. These reagents are hard to remember, the sodium bisulfite and water. It's just tricky. Like, this is just going to be something to memorize, sadly. This makes a vicinal diol, also called a glycol. And the important part about this reaction is that those OHs are added syn to each other. Now, back in lecture 7, we learned a way of making a glycol where the OHs were anti to each other. What was that way? From an epoxide. So we could have made this product over here, the anti version, from this epoxide in like H3O plus, or there's a version of it we could have done with NaOH. Either one would work. And that is going to make the anti version. So you've now learned kind of 2 ways of making these glycols or vicinodiols. The other kind of thing I will tell you about this that's a little bit weird is, what if you wanted to go on and do an acetal formation with like a ketone? Do you think that it's going to be easier to form an acetal with a glycol where both of them are the same direction, or where they're opposite directions? Which is going to be easier to make an acetal? The same direction. So like, let's say I added this ketone here. What we would get is this acetal. And here we can do it because these going the same direction make it easier to form this 5-membered ring. If one was on a wedge, one on a dash, it would be really hard to make a ring like that. It would make the ring strain really big. And so only this syn version will go and make a acetal. Okay. I mean, the reactions, certainly. You will probably have some sort of Grignard. Like, they're just all part of the kind of the pantheon of reactions. Are we going to, like, probably test you on enone 1,2 versus 1,4? Not explicitly. So you probably don't need organocuprate, but, like, reducing a carbonyl, 100%. Yeah. Last one here, this is my favorite reaction. I just like her. I just think it's neat. It's making an epoxide. This is MCPBA, which is this big molecule over here, which we'll talk a little bit about in the next lecture. What? Oh yeah, I just think they're neat, and I was like, oh, she's a she, they. Yeah. So, I just think these arrows are just cool. Like, this is such a weird, like, idiosyncratic, this is a one-step mechanism, and that, like, it's the whole mechanism makes the product. It's from this, like, peroxybenzoic acid. I just think it's neat. We don't test these arrows because it's a one-step reaction, so it would be a really basic mechanism question. You just really need to be able to use it here to form an epoxide. So now we have 2 ways of forming epoxides. The lecture 7 way from a halohydrin, and here from an alkene. There are some other ones that I'm not really touching on. I'm not touching on the carbenoids. I'm not touching on the H2 palladium on carbon, mostly because you don't need the mechanism for that one, and carbenoids are just kind of their own separate little thing. They're on the big review sheet, so that's there. I am at 11:29. I need to talk about Wittig. I'm going to go 8 minutes over, and I apologize for going 8 minutes over, but the Wittig is like one of the most, it will 100% appear in either a mechanism or a synthesis or both on exam 2 or the final. It's one of the most important reactions in the class. So, I'm going to talk about it. If you need to leave, that's totally fine. Again, I'm recording this, and so it will be posted. You can watch it later if you want. Truly, my key idea version of the Wittig reaction is the Wittig reaction is a powerful way to make both a carbon-carbon single bond and an alkene at the same time. So it accomplishes a lot of chemical work that up until this point has been really hard to do. The basics of this reaction is it takes a ketone or aldehyde with this functional group that we call an ylide, where we have a negative charge on a carbon, and then we have this positive PPH3 right next door. And what it does is it essentially glues these 2 ends together. So the thing that you are not seeing on this ylide that is there is a hydrogen here. And this R2 group in the hydrogen becomes glued together with the R1 and the hydrogen from the other molecule, making the alkene. And specifically, it likes to make Z alkenes. You don't need to really know the reasons for that, just know that it makes Z alkenes. This reaction, I think Tim calls it like the switcheroo or something. I call it the Boxy Boy reaction, just because there's a box that's formed in the mechanism. I think it's really cool, and yeah. So the Boxy Boy. It's just very like, ooh, suave, sleek, fancy Squidward. It's one of only 2 reactions you learn in this class that can make a double bond, a carbon-carbon double bond, and the other one is like the E1, E2 elimination. The other thing is, with E1 and E2, it was very hard to make terminal alkenes. Why was that hard? Carbocation stability? Well, I mean, with E2, you don't have a carbocation, so that's not exactly it. There's a rule. What was our rule with alkenes? Yeah, someone just needs to yell it. Zaitsev's rule. So Zaitsev's rule said that if we had the option of making this alkene or this internal one, we always do the internal one because it's more favored. So with the Wittig reaction, it has now become really easy to make terminal alkenes. Like, let's say you wanted to create this alkene here. You could make your aldehyde a 1 carbon unit, carbon here with 2 hydrogens. And this is formaldehyde, that's its name. And you can make this your ylid. And then here, that CH2 would become the CH2 on the end. Or you can make the CH2 here your ylid, and then that becomes the CH2 on the end, and this is from your carbonyl. But this is kind of synthesis strategy-wise. Let's get into the mechanism real quick. So first of all, making an ylid. Sometimes, like if you're trying to do a Wittig reaction and you want to just pull an ylid out of thin air, you can do that. But other times you will start with a molecule and want to turn that into an ylid. So this is how. You start off with an alkyl halide, and the first thing you add is PPH3, which does an SN2 attack. Second thing is you are really close to the ylid, you just need a negative charge on the carbon, so you add a strong base, and we always use N-butyl lithium. So N-butyl lithium is going to go and deprotonate this, and now we are at the ylid. Cool. The actual mechanism here is once we have the ylid, it is going to be our nucleophile, and it's going to attack the carbonyl, push up. And then we have this intermediate where we have a negative charge on oxygen and a positive charge on the phosphorus here. These charges are opposite in charge and right next to each other, and so it's going to do an attack and make it neutral. This is our box. This is like the fancy weird thing of the Wittig reaction. And here we collapse our box. So the electrons that were in this CO single bond come and form a double bond here between oxygen and phosphorus. And the electrons in the carbon-phosphorus bond fold down in and make the carbon-carbon double bond. And that's how we get out the alkene and then our like byproduct here, which has the PO double bond. This is a great mechanism question. This is a great tool for synthesis. It appears a lot. So I would know this reaction really well. The last thing to end off on is going to be trying to do some disconnection practice or connection practice with the Wittig. So I'm going to do this first one with you. The way that we would disconnect this into our starting materials, there are kind of 2 options for it. But we know that we are going to have to split this alkene because this reaction makes the alkene. And then one side needs to become the ylid, one side becomes the carbonyl. And so let's do both versions. We have option A here, where I'm going to make that top little CH2, the carbonyl, and I'm going to make the whole bottom thing the ylid. So that's option A. Option B, I make the bottom thing the carbonyl, and the top thing the ylid. Now another thing that we could ask you for this, for our 2 options here, is which one would be the better synthesis route? To answer that question, we have to look at the ylid formation reaction. So over here, do you remember to form the ylid, we had to do an SN2 attack? What that means is ylids that are less substituted are easier to make. So between this methyl ylid and the secondary ylid, which one's going to be easier? The methyl. So this is going to be our preferred way of making it. And it's just because the ylid is going to be faster to form. You could do it the other way, we would not count off points. So try this disconnection with getting the two options, and then try connecting these two, and that will be it for section. So for this middle disconnection, we wind up with two ylids here. This one, which is technically primary, and this one is technically secondary. Which one would be easier to make? The primary. So this disconnection is going to be the better one to start with synthetically. For the other one, it's just practice gluing the two things together. And so we would form this. Here we don't have to worry about E or Z because it's the same on both sides here of the double bond. But if you had a choice, you would want to make the Z. Thank you for letting me go 8 minutes over. That's all I have for section today. I hope this was helpful. Please let me know what questions that you have. I'll stick around and be answering some questions. And then annotated things and key and video should be posted in the next day.